Prototyping a single AI agent in a local Jupyter notebook is trivial. You write a prompt, attach a search API, and watch it work. But deploying that same probabilistic logic as a reliable, autonomous workflow in a production environment is an entirely different engineering discipline. At scale, these systems fracture. They suffer from non-deterministic routing, where the model chooses the wrong tool, infinite hallucination loops during self-correction, and prompt bloat resulting from attempts to force specific behaviors through natural language alone. Stability can be engineered into these systems. This end-to-end autonomous pipeline scrapes live news, generates a script, synthesizes audio and video, and opens a finalized GitHub pull request with human intervention. The LM Studio interface triggers this pipeline through a natural language request via an MCP client. The system maps this request into strict JSON parameters for the downstream API. An HTTP 202 response confirms the handoff, and the workflow begins autonomous execution. Reliable autonomy requires a shift in perspective, moving away from the concept of omnipotent agents and treating large language models as constrained software nodes within a deterministic architecture. A common architectural error involves equipping a single agent with a wide array of tools to handle a sequence of distinct tasks. This overloaded agent configuration includes both an extraction tool and a publishing tool. This forces the model to reason about tool selection and execution order simultaneously, increasing token consumption. This cognitive overhead introduces routing ambiguity. In production runs, this complexity leads to missed tool calls and unpredictable execution paths that are difficult to debug. Applying the single responsibility rule fixes this. By decomposing the workflow into two distinct agents, each with exactly one tool and one task, the system removes the model's need to navigate tool selection noise. Multimodal generation presents the same risk. This agent is asked to both structure a VO3 JSON video prompt and execute the generation API. Mixing planning with execution typically results in malformed schemas or hallucinated file statuses. The solution is a physical boundary. The JSON builder agent is isolated, responsible only for returning a valid schema. The actual video generation is handled by a standard code function, ensuring deterministic API interaction. This logic extends to core infrastructure. There is no engineering requirement for a language model to perform standard software operations, like opening a Git branch or writing to a database. These terminal logs show the result of forcing an LLM to navigate the MCP protocol for GitHub operations. The workflow fails with resource not found errors, which developers often try and fail to fix with increasingly fragile prompt instructions. Removing the agent entirely for these tasks restores stability. This pure Python function handles the GitHub PR creation directly, bypassing the ambiguity of the language model loop. Moving probabilistic tool calls to deterministic pure functions for all infrastructure tasks provides the stability required for production-grade software. Content generation introduces different risks. Relying on any single language model in production exposes the system to model drift and the specific biases inherent in that model's training data. A consortium architecture mitigates this risk. 3 specialized LLMs, Gemini, OpenAI, and Claude, process the source data in parallel, generating 3 independent drafts from the same grounded facts.
These agents operate under strict formatting and grounding rules. Explicit directives, such as the prohibition against inventing facts, ensure the drafts remain anchored to the provided research materials. Despite identical inputs, the models produce divergent phrasing. Llama generates structured, concise summaries. OpenAI produces narrative-heavy content, and Gemini focuses on conversational flow. This diversity captures multiple semantic dimensions of the source material, providing a broader range of high-quality drafts for the final output. The challenge is that this diversity can introduce factual inconsistencies or contradictory statements between the different model outputs. A reasoning agent acts as the final auditor. Its role is strictly to compare, resolve conflicts, and consolidate the parallel drafts into a single authoritative script. This agent cross-validates the parallel drafts, looking for points of consensus among the different models to determine what information is most reliable. This process identifies and removes speculative data or hallucinations that are unique to any single model. ensuring the final script reflects the shared facts. In production, responsible AI relies on an ensemble architecture that uses rigorous cross-validation to mitigate the reasoning errors and biases of individual models. The deployment layer requires similar separation. The Model Context Protocol, or MCP, has become the standard for connecting LLMs to external data and tools. However, embedding core workflow logic directly inside an MCP server is a significant architectural anti-pattern that creates brittle, difficult-to-scale systems. The MCP server must remain a thin adapter. Its only function is to forward calls to a standard REST API that houses the actual agentic orchestration logic. This decoupling extends to the prompts themselves. Agent instructions must be pulled completely out of the application source code. Storing prompts externally allows domain experts to update agent constraints and safety rules without requiring engineers to redeploy the backend services. Finally, production systems require the physical boundaries provided by containerization. Packaging the MCP adapter and the workflow engine into isolated containers eliminates configuration drift and ensures consistent execution across development and production environments. Orchestrating these containers with Kubernetes allows for independent scaling. Inference-heavy reasoning nodes can be scaled up during high traffic periods without impacting the resources of lightweight scraper functions. Scalability is a function of strict boundaries, keeping prompts out of code, logic out of adapters, and components physically isolated. Tracing the macro-level architecture reveals the complete flow, from initial web discovery through the reasoning consortium to the final GitHub PR. The autonomy of the overall pipeline increases in direct proportion to the constraints placed on its individual nodes. Reliability is found in specialized, predictable software units. Building agentic AI systems is no longer an algorithmic research problem. It has become a rigorous systems engineering discipline. You can access the open-source GitLab repositories to pull the containerized MCP servers and workflow logic and see these architectural principles in action. Ensuring an AI system works deterministically on every production run requires committing to the rigor of pure functions, modular design, and strict architectural boundaries.